Thank you, Luca. I appreciate the opportunity to speak here today, and I don't think the audience members here who already mistook me for Betsy once this morning, this will confuse people even more, so we've switched this afternoon. So what I'm going to talk about today, the motive behind it is for looking at a problem, the regularity problem, in the case of the Lemay system of elastostatics for curvilinear polygons in 2 dimensions. So just to remind you of the regularity problem, we are seeking a vector value function, in this case u, that solves the Lemay system in a given domain omega with prescribed boundary condition equal to a function f in the space LP1 of the boundary, where we also seek the additional order of regularity that the maximal function of the gradient of u will also lie in LP of the boundary. Here, again, I'll be working on curvilinear polygons in 2 dimensions. L is our Lemay operator, which I will remind you of on the next slide, and the space LP1 denotes the space of LP integrable functions on the boundary whose tangential derivative is an LP. Okay, so I just want to remind you of the Lemay operator in 2 dimensions, given as follows. The lambda and the mu are constants known as the Lemay moduli, satisfying those 2 given conditions, that mu is greater than 0 and their sum is greater than or equal to 0. And secondly, I have on the bottom of the slide the fundamental solution, which is a matrix value solution to the Lemay operator, given as follows, for I, j equal to 1 and 2. So you see it depends on the Lemay moduli here. Here the delta sub ij is the normal delta symbol equal to 1 when I equals j and 0 otherwise. Just a brief overview, I won't even be able to mention all of the results in this direction, but some of the history of the study of the regularity problem in Lipschitz domains. Several mathematicians, Faves, Kenning, Vercoda, Gao, uncovered the solvability of the LP Dirichlet and LP regularity problems for p close to 2 in dimension d greater than or equal to 2. Pfeiffer and Vercoda worked on the LP regularity problem in 2 and 3 dimensions and established a sharp range of well-posedness indices for p between 1 and 2 plus epsilon. Zhongwei Shen at the University of Kentucky, he has done some work in higher dimensions, working on the LP regularity problem, establishing the following range of indices where the regularity problem is well posed. And in a preprint, Shen and his student, Joe Kilty, have been examining the duality between the LP Dirichlet problem and the LP prime regularity problem for second order and higher order elliptic systems, where p prime is the conjugate exponent to p. Now the types of domains I'll be working in, again, curvilinear polygons, but via a localization argument, we're able to reduce the problem to looking at the regularity problem on sectors in 2 dimensions, infinite sectors of aperture theta between 0 and 2 pi. And these types of domains fall under the category of a special Lipschitz domain, that is, it's a domain lying above the graph of a Lipschitz function. Okay, keep looking there because it's too big to read. So if we let omega be a subset of R2, I want to now discuss the layer potential operators that I'll be using in this work here. So if we fix a vector value function from the boundary to the reals, we can define our single layer potential operator, I denote with a script S, acting on G to be the following integral. We're integrating over the boundary between the fundamental solution of the Lemay system against our given function G, and that is for x on the interior or the exterior, so away from the boundary. And then we have what we call a boundary version of this single layer potential operator, I denote with a block S, and now we're taking our x to be taken from the boundary of our domain, which will introduce a singularity, so we have to consider this integral in this principal value sense. Okay, now some properties of this layer potential operators, why they're interesting to us in this problem, is that the single layer potential operator satisfies the Lemay operator, and it also has the following jump relation on the boundary. So if you approach the boundary from the interior or the exterior of your domain in a non-tangential way, the operator, actually, the single layer potential operator has no jump. So you're going to, the interior version, the script version, as you approach the boundary, equals the boundary version in the limit sense. So if we have these nice 2 properties of it, then it is natural to start to look for solutions to the Dirichlet problem of the form, a single layer potential operator acting on some function G. So that's exactly what I'm going to do. I'm going to seek my solution U to be of this form, of the single layer. And if I want to do that, then I need to, of course, match my boundary condition. And due to the Job relation, I need then, for the boundary version of my single layer potential operator acting on this, right now, unknown function g, to equal our given boundary data f. Okay, so f is the prescribed boundary data that's given to us in the problem. G is unknown. And, in some sense, you could think of, we could figure this out if we could somehow invert this operator S, this boundary version of the single layer potential operator. So that's what we're interested in finding, and that is obtaining sharp invertibility properties for this operator S, which acts from LP of the boundary into LP1 of the boundary in the class of Lipschitz domains. Okay, now if I'm going to discuss the invertibility of an operator, then I've now reduced this to a spectral question. So I remind you here that if we have a bounded operator from a Banach space, then we define its spectrum on the set to be the set of all complex numbers, W, such that W times the identity minus our operator is not invertible on that space. And we know for each p between 1 and infinity that this boundary version of our single layer potential operator is bounded from LP into LP1. So I am going to be interested in looking at the spectral properties of this operator S, again in our class of Lipschitz domains, with our data taken from the space LP of the boundary. The method we use to examine the spectrum is that of Mellin transform analysis. So here I've defined above the Mellin transform of a function f. If you have an infinitely differentiable function with compact support, we define this Mellin transform to be the following integral on the positive real line. And we say that an operator is of Mellin convolution type if the operator acting on a function f at a point x is equal to an integral of the following type. We have some sort of kernel of x over y times our function f of y, and the measure is dy over y. Now why is this interesting to us? Well, in the case when we have this nice Mellin convolution type operator, and we look at the operator acting on a function on the Mellin side, okay, just similar to how a Fourier transform acts, it's going to pull apart the convolution as a multiplication on the transform side. So we're going to be examining spectral properties of the operator by looking on the Mellin transform side, and then we can focus on looking at spectral properties of this kernel function little k. Just kind of an overview of the idea behind this. So we recall that we're working on infinite sectors in 2 dimensions, and in this case, actually, unfortunately, the operator under examination, the block S, is not exactly of the Mellin convolution type we would like to apply this analysis. However, if we take a look at its tangential derivative, we do fall under these special conditions. So we are going to employ the Mellin analysis techniques I just discussed to examine the invertibility now of the tangential derivative of the boundary version of the single layer potential operator. And since it's a tangential derivative, we'll now be acting from LP of the boundary into LP of the boundary. Okay. Now what you see on this slide here is actually a picture of the spectrum of this operator. So I'm, again, examining the spectrum of the tangential derivative of the boundary version of the single layer potential operator. In this picture, I'm taking a sector of aperture theta equals 2 pi over 5, and I've set my Lemay moduli to both equal 1. And what you see in front of you is actually the complex plane. So this laser is not very powerful, but down the middle vertically is the imaginary axis, down the middle horizontally is the real axis, and every point on the curve is a complex number that is in the spectrum. So if you pick a point on this curve anywhere on the black line, then that complex number times the identity minus my operator is not invertible. Okay. Now, one thing I want to point out, unfortunately, the error in I was doing this in MATLAB has given me this vertical line down the middle. It actually should not be there. There should just be 2 sort of clovers here. So again, we're interested in just inverting our operator, partial tau of S, so I want to know whether or not the point 0 is in my spectrum. Okay, and unfortunately this picture is a little floppy, but in fact the point 0 is not in the spectrum here. So we do have invertibility in this one particular case. Again, these pictures aren't necessarily to prove anything, but they're kind of neat to look at. Here's just another picture I created. Now I've taken my angle, I've taken my sector to be of angle pi over 6, so I've made it narrower. Again, lambda mu equal to 1, and you can see the spectrum, the shape of it changes. The spectral radius here has also gotten a bit smaller. Okay, So going back to this Mellin analysis technique, I applied the Mellin transform to my operator. And the fundamental solution, remember, is matrix valued. So I'm going to end up with a large matrix on the transform side. And I end up with a 4x4 matrix. Each 2x2 corresponds to looking at different placements of points on my sector. So whether or not they're on the same side of the sector, opposite sides, and there are 4 different combinations. And so we can evaluate this, the Mellin transform, and what I have on the bottom here, all the values. This is a large matrix, it's 4x4, but the entries are complicated. So the V entry I've given below, the A entry is the following, B, and C. So it's a large algebraic computation in the 4x4 matrix. And how we proceed from here is to set the determinant of this matrix equal to 0 and solve for Z. So what complex values make this equal to 0? And the resulting two, we actually end up with 4 equations after a lot of algebraic manipulations. And so we end up with the following 2 equations, that the determinant will be 0 when either of these 4 equations, there's a plus or minus on both, is satisfied. And this complex number we're looking at, Z, is actually equal to 1 over P. This is our index of integrability, plus IXC, where P lies somewhere between 1 and infinity, and C is a real number. And so, focusing on these 4 equations, we're able to first establish that the complex part of Z must be equal to 0. So the only solutions are real valued solutions. And then we're looking to narrow down the possible p-values where these are solved. And that's going to show us integrability indices where the determinant is 0, and this is where the operator will no longer be invertible. And we call these the critical p-values. Okay, so these are the p-values which are going to make this determinant equal to 0, and then therefore cause the invertibility to fail for our tangential derivative, which of course we then want to relay back to the invertibility of S itself. So here's the theorem of our work. This is joint work with my PhD advisor, Irina Petria. If we let omega be an infinite sector in 2 dimensions with aperture theta between 0 and 2 pi, at the top here I've excluded the case theta equals pi. If you think about that, that sort of corresponds to the smooth case, since that would give you a straight line. Then we come up with actually 2 critical indices, P1 and P2, that we are able to capture inside these intervals, depending on the aperture of our sector, where the invertibility of our our operator S from LP into LP1 fails to be invertible. So it's invertible for all P's, minus these 2 P1 and P2 values, and they just switch depending on whether your angle is less than pi or greater than pi. And it is well known, but we stated here that when you have the special case theta equals pi, you're in the smooth case, and you're going to have invertibility for all P between 1 and infinity. So because of the algebraic, complexity of these equations, we're not exactly able to solve, particularly for P1 and P2. We have them captured in these intervals, but you can map, what's happening, for instance, to this first critical p-value. So what you see in this picture here is my angle theta is moving over to the right, it's equal to pi, and to the left it's going to 0. So this is as my angle is getting sharper and sharper, and what you see is that first critical p-value seems to be decreasing to 2, approaching 2 from the top. And so this is just a conjecture, a picture that we've made in MATLAB, but this is the current focus of this work, the project as we're finishing it up. We're not able to explicitly solve for the p-values because of the complexity of the equations, but we would like to get as many properties about them that we can. And for instance, this property here about the monotonicity of this first critical p-value, looking as it approaches 2 from the right as theta approaches 0. And in fact, this is a conjecture that we have, and it's hard to prove because of the huge equations that you're dealing with. But what we are doing is bringing in a collaborator, Warwick Tucker, who's at the University of Uppsala, or Bergen right now, perhaps, I believe. And he uses interval analysis techniques, which are computer-aided techniques that can sometimes overcome when you end up with these roadblocks from algebraic problems. So using these techniques, we're hoping to prove that this P1 value is in fact monotonic and approaching 2 from the right. And just briefly, it's not my area of expertise, but to just briefly mention what these interval analysis techniques do is Warwick Tucker and people in this area use computers to prove things in a mathematically rigorous sense by doing computations on computers over intervals rather than points. And intervals in 2 dimensions or boxes in higher dimensions. And by doing this, he's able to incorporate the errors that are accumulated by a computer and to account for them. So by doing this work over sets, then we're hoping to be able to prove, for instance, this monotonicity of the critical index. And I think that's huge stuff. So thank you for your attention.
Do you have any questions?